This is a first-year chemistry lesson I like to call Magic of the Mole Hole. It impinges on the teaks performing stoichiometric calculations, including determination of mass relationships between reactants and products, calculation of limiting reactants, and percent yield. What does the mole do? Mole is a measure of chemical quantity. 1 mole of one substance has exactly as many atoms, molecules, or formula units as 1 mole of any other substance. So you're counting here. Now the masses of the 2 moles might be quite different. For instance, hydrogen molecules all together in a mole are 2 grams, whereas oxygen is 16 times larger, 32 grams. Substances, however, react, chemical reaction, in molar ratios that are always ratios of small whole numbers. 2, 3, 1, 1/2. For instance, 2 grams of hydrogen will react with 16 grams of oxygen, but 2 moles of hydrogen will react with 1 mole of oxygen. And you see, that's a simple whole number relationship. So inside the mole hole, masses are no longer relevant. We dig into the mole hole by simply dividing each number of grams by the molar mass. Everything then in the mole hole, in the chemical reaction, will react in mole ratios of small whole numbers. This makes any computation we do very much easier. For example, we know that 2 moles of hydrogen react with 1 mole of oxygen. The 2 gases react to form water vapor. And the equation shows that. 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of water vapor. Outside the mole hole, however, if we're forced to use grams to describe chemical reactions, then here's what we have. For instance, sodium reacting with chlorine, 23 grams of the former react with 35.5 grams of the chlorine, and they form 58.5 grams of sodium chloride. Fine. Can you do anything with that beyond the sodium and chlorine? Well, the answer is no. That's what we have. And if we study the potassium-chlorine reaction, we see 39 grams of potassium reacting with 35.5 grams of chlorine, forming 74.5 grams of potassium chloride. Do you see any relationship between these 2 sets of numbers other than they both use 35.5 grams of chlorine? Really not. We miss the family similarity, realizing that on the periodic table, sodium and potassium are right on top of each other in the same chemical family. However, when we are using moles, that is, if we simply dig down into the mole hole by using that molar mass conversion factor, divide by the number of grams per mole, divide grams by grams per mole, we get moles. We see, oh, there is the formula. 2 moles of sodium react with 1 mole of chlorine to form 2 moles of sodium chloride, and by the same type of mathematics, dividing by the molar mass, 2 moles of potassium react with 1 mole of chlorine to form 2 moles of potassium chloride salt. Well, you can see the family resemblance here. And this actually enables us to picture in this family what is going on at the sub-microscopic level, below the level that we can actually see anything. We can imagine this going on. There's 2 atoms of either potassium or sodium reacting with 1 molecule of chlorine, and that's before the reaction. The reaction occurs, there's a huge flame, and now we've got 2 moles of either sodium chloride or potassium chloride, depending on which metal we may be using. Now we have a simple chemical language that in fact people all over the world can understand. If you look at a Japanese textbook, these two equations are what you will see. Now, you might not see much else if you don't speak or read Japanese. You might not be able to tell what else they're saying, but you'll be able to read the chemical formulas and the equations. And what does it mean? It means 2 moles of either sodium or potassium, and behold, lithium or rubidium or cesium, they react the same way with 1 mole of chlorine to form 2 moles of the salt. A RICA table can be used to help us visualize the mole interactions. They're maps through the mole hole problems. Here's a sample RICA table for the oxidation-reduction reaction we just studied. 2 moles of potassium react with 1 mole of chlorine. How many moles, here's a problem you might see, how many moles of KCl would be produced by reacting 0.452 moles of potassium with excess chlorine gas? Well, here's how we would show that. The RICA table has 4 lines. The reaction on top here, the initial quantities in moles or millimoles, the change that occurs during the reaction, and then the after picture, how many moles of products. And if we have reactants left, it'll also show that. So let's see how we do this. There's the problem on top. So we're going to put 0.452 moles of potassium in the initial slot. We have excess chlorine next to it, and we don't start off with any potassium chloride. Now what? Oh, we have the equation on top that tells us how much chlorine is needed for 2 moles of potassium. It's 1 mole. So we would divide the number of moles of potassium by 2 to get the number of moles of chlorine, because we need twice as much of this as we do of the chlorine. And since the coefficients here are 2, 1, and 2, we will end up with also 0.452 moles of the salt, potassium chloride. And so if we simply do the math, then we see that whatever the excess was, first of all, we lose all the potassium. That's our limiting reactant. We're left over with whatever beyond 0.226 moles we had initially of the chlorine, and we're left, of course, with 0.452. You'll notice the only place that signs show up is in the change. Negative here, negative there, and positive there. Negatives on the reactants and positive on the products. RICA tables also give us a way to solve more complicated questions that we might see. For instance, suppose we mix 0.689 moles of potassium with 0.689 moles of chlorine. How much potassium chloride would we get? Oh, okay, well, the initial is fine. We don't have any end product, and we have equal moles of potassium and chlorine. This says that 2 moles of potassium require only 1 mole of chlorine, so 0.689 moles of potassium will require only half this much of chlorine, or 0.345. So we'll lose all of the potassium, half of the chlorine, and of course we'll produce, because of the 2, 1, 2 coefficients, we'll produce 0.689 moles of potassium chloride. And therefore, we simply add these up, and of course this minus that is 0. This minus 0.345 is 0.344, with of course uncertainty in the last digit, and we have 0.689. You'll notice a negative here, and a positive there. And so this helps us with questions like, how many moles will be left over? And what's the excess reactant? Well, obviously, this is the excess reactant. So it gives us the answer to the problem if the problem was asking for how much product. If the question was asking us how much excess reactant and which is it, So it helps us answer questions like those very, very easily. So, RICA tables and the mole hole. You must always begin with a balanced chemical equation. You draw the RICA table. It's only valid in the mole hole, so it only works with moles. If you've got gases at equal temperatures and pressures, it also works with them, but we won't go over that at this time. You put the initial known quantities into the I column, and the change column then comes from the chemical equation, determines the changes in the initial quantities. It's negative for the reactants and positive for the products. And then at the end, you add the I quantities to the C quantities to find the after quantities.